Sorting. That's a fundamental computer science problem. Not math problem, but computer science problem. Now we do need some math to analyze and figure out what's going on, but sorting is one of these basic blocks of computer science. We talked about last time about searching, and we did chunk search and binary search and so on and so forth. Sorting, they're like a plethora of sorting techniques. We're not going to do all of them. We're going to do the basic ones. So we need to look into merge sort, insertion sort, selection sort, bubble sort. That's kind of the regular stuff. Of course, we're going to add our own things to it. That is binary search trees. They call search trees, but they're pretty good for sorting. Bucket sort. I don't know how come we managed this, but bucket sort originally was intended in my head as an honors thing. And somebody asked me last week, hey, give me a problem for the homework, the regular homework. So I say, there you go. And now bucket sort is a problem for everybody. Anybody looked at 5.2 in the homework, the current homework? Yeah, that's another thing, right? It's going to become very painful over the weekend, I'm sure. It's a good time for me to take vacation, like I'm out of Piazza, right? This weekend. And by Monday and Tuesday, pain is going to settle with that 5.2. We should make it optional. We put 2 stars to it because all the stars, right? I wonder if the regular students all the stars. What else can we do? If we have time, counting sort, we're probably going to have time for it. I already put something earlier, like a preview thing, see-through thing on binary search. If you saw on the website, there is a link called Radic Sort. I don't know how many people looked into that. We can look into it. There's shelf sort, and there's something important as a data structure that I really want to have time to do it. Let's see how far we can get into these methods. Now, not everything is going to happen today, obviously, but sorting is a big deal. Analysis of sorting is a big deal. And particular analysis of the input is a big deal. Sorting can have very different behaviors depending how the array or the list that you want to sort behaves. So that's going to be a thing that we need to look into it. The data, for now, is going to be an array or a list. Like, what is it that I'm sorting? To be clear, an array is a continuous chunk of memory. 1, 2, 3, 4, up to n. Of course, this is a of 1 all the way to a of n. And it's really easy to access an index in the middle. Access a of any j is constant time. When I say theta of 1, for now, I'm not rigorous. I mean generically, in one shot, in one operation, I can access that value of the array. The reason I know how to access it is because I know what the beginning of the array is. And I know every element, how much memory it takes. All the arrays, even if they don't give you an explicit value, like in C++, you declare the array to be every value is 4 bytes. In some other languages, you don't declare it like in MATLAB, but MATLAB knows internally exactly how many bytes have for each value. So because each value has 4 bytes, suppose I want to access that's a of 0 right here in memory. It starts at 0. And suppose I want to access a of 17. How do I do that? Do I know exactly where in memory to go? Where is that a of 17 value? Yeah, I know, because I know a of 17 here. How many bytes do I have to go to a of 17 if each value is on 4 bytes? 16 times 4, right? I know exactly the memory address where the 17 value is going to be. So this random access with arrays, because it's always a continuous chunk of memory, it's very, very fast. Of course, that's a problem, for example, if you want to increase the size of the array. You just declare an array of 100 integers, you have the memory for it, and out of a sudden you say, oops, I need 3 more values. I forgot. You can just add 3 more values to that chunk of memory because that may be something else in the memory right there, right? You don't know what's coming after this array in the memory. So you would have to find the space for 103 values somewhere else in memory and copy the whole thing over there. Because there's no way to say, I'm going to use that memory that comes right after. You don't know what's in it. It used to be that operating systems let you do that. So people got really funny results. By overwriting after the memory that was allocated to the array, they managed to break into cryptography systems because they speculated what might be written in there, and they overwrite it with an overflow, and that caused problems. Now, modern operating systems wouldn't let you do that. If you declare my arrays from here to here, as soon as you want to write here, they say, sorry, that's not possible. Because that's not your memory to write on. How about a list? A list has the same values, a of 0, a of 1, a of n, but they're not in continuous space of memory. There is a linkage mechanism between those values. They could be spread all over the memory, the list, but for each one, I know there is a way to go to the next one. And sometimes this linking is back. Okay, I'm going to do the previous one. But that's really easy to expand. I want 3 more values. I tell my operating system, give me another object in memory, anywhere, doesn't matter where, right? And I'm just going to make it a new object. All I have to link it properly with those pointers, and I've got my list increased. I don't have to reallocate the whole list and copy it all. So that's good. Problem is in here, I cannot access anything in the middle. I know where the list head is, but if I want a of 17, how do I do that? How do I access the 17 element in this list? Yes? I go from the beginning, jump, 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 17 times until I get to the 17 element. Now there are ways to complicate a list, a skip list, to make that much faster, that access. But that would be a complicated structure. Basic list doesn't have it. So between a list and array, you can see the advantages and disadvantages. I want to establish that before we go into sorting. As part of the sorting themselves, I would like to do a little demo, just to have a little bit of fun. Last day of fall, right? So I need 8 volunteers. Okay, so 8 people. You're not going to do anything. I'm not going to ask any questions. You're just going to play the role of being the values of the array. How about that? 8 people. The first 8 to come here, please. I need 8 because there's 8 values in here. I'm not going to ask you any questions. This is not an exam of whatever kind. But it may take a while, okay, to do this right. So the input with the array is marked. So A is the first, B is the second, just to have an order. So you guys stay in line. How many we got? 2, 4, 6, 7. One more, please. 2, 4, 6, 7. One more. Anybody? Whoever comes first. All right. So I will be the sorting algorithm, the sorting machine. Hopefully, I do my job good. And they are the input. An array. Let's select an array, but it could be a list. So here's the A, and that's inside it is a value that needs to be sorted, but we don't look at it right now. B, C, D, E, F, G. So inside everybody has a number.
Yeah, you want to like switch that?
Hold on. So I'm the processor, right? I'm processing this, and I got this array to be sorted, right? Array comes in order. So I'm gonna do insertion sort. That is, in the list, is the second one, right? So insertion sort works like this. I think some of you've seen it, but I'm not assuming that. Maybe you've seen it for the first time. I look at the first value, 6. Since it's the first value, I say, okay, great, 6, it's good. It's a first value. Let's say I put the 6 in here, right? Somewhere. Then I look at the second value, and I say 3. You know, I think, hold on. I want you guys to move on this side to kind of have the ABCD in the array order, right? So that would be 1, 2, 3, 4. So let's kind of line up in the other way. So I could do this in a visual. Okay. So I've seen 6, right? 6. Okay. Let's say here, leave it open. That's a 6. Now I'm reading the next value in my array. That's a 3. What I do, I put the 3 right next to the 6. But then I wonder, should I swap those? Are they in the correct order or not? I want increasing order, say, right? Should I swap them? Yes. So 3, I move 3 over 6. Now I get the next value. What is it? 7. That moves right next to the 6. Every new value, I put it, you know, right next to the. I currently have a 2-value array. Now I'm reading the 7. I just look at 7 and 6. That's it. Because these guys are already sorted. 6 and 7, are they good? Next value. 2. Okay. I don't look at those 2. Let's close this. I know. I look at the last one. So I'm saying 7 and 2, are they good? No. Swap. Now I look at those 2. 2 and 6, are they good? Swap. Now I look at those 2 and 3, are they good? Swap. Am I good? So far. Insertion sort means I pick the next value and I'm going to insert it in the proper spot. Little by little. So now I'm looking at the next value. What do I see? 4. 7 and 4? Yep. Swap. 4 and 6? Swap. 4 and 3? If 4 and 3 is good, do I need to compare 4 and 2 or anything like that? No. I found the spot. He's in the right spot right here, right? This is sorted already. I'm looking at the next value. What do I see? 8. I look at 7 and 8. Is that in the right order? Right. Do I need to worry about the rest? Because this is already sorted, right? So 8 is in the proper spot right here. I don't have to compare with the previous values, just with the 7. Next value, 1. This is going to be a problem, the 1, right? So 1, swap with 8. Keep checking. At any moment in time, I only look at those 2 values. I'm not checking 1 all the way to the front somehow. 1, swap, swap. 1 and 4, swap. 1 and 3, swap. 1 and 2, swap. Definitely in the right spot right here. Right? I know it's in the right spot because it either reaches the end or when I compare with the previous value, it's bigger than it. Next value, 5. 5 with 8 has to swap. 5 with 7 has to swap. 5 with 6 has to swap. 5 with 4, no swap. Is it good? That's insertion sort. Let's redo this last step. Let's take the 5 again, say this is sorted. And now I'm wondering more like analysis question. In the best case, suppose I don't see this 5. In the best case, how many swap am I going to make? 0, but I still have to check 1. To determine that I need the swap or not, I do 1. In the worst case, how many swaps I have to make? And all of them, if she is the 17th element, I may have to do 16 swaps. Right? But for the next element, I may have to do +1 swaps. If somebody swaps all the way to the beginning, that value increases, right? For the second person, that's 1 swap. For the third person, that's 2 swaps. For the 16th person, that's 15 swaps, and so on and so forth. How about on average? If I tell you, I don't know this number. On average, how many swaps are we going to make? Of course, if I see the number, I can tell immediately that's going to be 3 swaps, right? But if I don't see the number, it could be no swap. It could be 7 swaps. What do you think the average will be of number of swaps? Like estimate? Yes?
N over 2.
That's just a guess?
Yeah, because it's like average, you either can go to the front or to the end. So somewhere in the average is going to be like the middle.
So I would like to prove that by the end of today. That if she has an equally chance of being smaller or higher than anybody else, perfectly random, that is, every swap has the probability of, say, 50-50, right? Because we don't know her number versus 8, it's 50-50 bigger or smaller. Her number versus 7, 50-50 bigger or smaller. On average, if every swap has the chance 50-50, I would like to say I could do 1 swap, 2 swap, 3 swaps, up to 7 swaps. This will be on average about 7 by 2. But let's see. Okay, are we all convinced about that? Insertion sort, any questions? I have a question. Do I really, what's my plan here? Now I see the value, 5. I know it's gonna go in here, right? Like I know post-mortem, I know. Is there a way to put it in here without doing 3 swaps? Like, what did I just do before? I did 5 with 8, 5 with 7, and then 5 with 6. Chill up here. I know that's the right spot because 5 is bigger than 4. But is there a different mechanism that will allow me very quickly to determine where the right spot for this number is? Not by doing repetitive swaps. So I look at her value, I have all this. This is, you guys can close. Suppose I'm not looking at their values. All I know it's in order. Can I determine, hey, this value belongs in here somewhere? Not by doing 3 swaps.
Just put it in the middle and then compare it.
I can put it in the middle and then try to move around in the middle.
You can keep checking from the end until you find the first value that's lower than the value you're looking for.
Right, but that's the same as doing swaps. Checking this and then that and then that. It's 3 swaps. I like the middle idea. That's more like binary search. Can I take advantage of the fact that this is already sorted? Is it always already sorted? So maybe instead of doing 1 swap, 1 swap, 1 swap, I look at that 5 and say, hey, compare with him. That's a 4. Is that too much or too little? Too little. Then compare with, the middle in here. That's a 7. That's too much. Right? Do binary search that way. And then I find the spot. What would the problem be with that? Are we all seeing what I'm doing here? I look for that 5 in a sorted array. I can find its correct spot right here very quickly, log n time, right? But what the problem is? Yes?
You still have to do swaps to move them one further and insert her.
Even though I can find her spot really quick in here, log n time, binary search. In an array, you cannot just put something in the middle of the array. You have to move either this part of the array or this part of the array. Remember, arrays you can access discretely, but you can't just put something in the middle. They're a contiguous chunk of memory. What if this would be a list? Would I be able to insert in the middle of the list something right away? Would I be able to find a spot? Why not? Why can't I do binary search in a list?
Because you can't instantly jump to any place in the list.
I couldn't compare with the middle of the list right away. Okay, so that's insertion sort. How about we do this again? Can we reorganize ourselves in the order of A, B, C, D? You first, but on that end. So yeah, you first, and then B, C, D. Who's B?
Hello.
B is after her.
He's over here this time? Okay.
B, C, D.
Oh, yeah, wait. We're on the left. We're on stage left.
Everybody got insertion sort, hands up. Insertion sort, hands up. Are we understood that how it works? We'll write it on the board anyway. I want to try bubble sort. Anybody knows how bubble sort works? Bubble sort. Everybody heard of bubble sort? How does it work?
You have pairs of people that you're comparing at a time? Right.
Yeah. Bubbles. Bubbles are the pairs that are in one order this way. Let's open these 2 values. Is this a bubble? A bubble is when it's in a certain order of the input. She's first, he's second. I1, I2. That's the first value, second value. But the order is not the one I want. Remember? I want increasing order. So is this a bubble? Okay, so. Now that's done. I keep going at those 2. Is this a bubble? 6, let me see, 6, 7. Is it a bubble? Is it a bubble?
Yes.
Is it in the correct order or incorrect order? Correct. Correct order is not a bubble. A bubble is an inversion, is an incorrect order. Is this a bubble here? 7, 2? So. How about this? 7, 4, is it a bubble?
Yes.
So. These values I'm not looking at anymore. 7, 8, is it the bubble? No. Good. 8, 1 is the bubble?
Yes.
Let's keep it in the way so people can see the 1. 8 and 5 is the bubble? That's all. Now, am I done? Why am I not done? I didn't go through all the possible bubbles. I went through some of them. Like maybe I can guarantee the highest element reach the end by one pass in the array. Do you think I can guarantee that? That the highest element reach the end? Because I keep going with the highest element, it was not at the end. But and I might have picked some other bubbles in the middle, but I could have more bubbles. Let's go from the beginning. 3 and 6 a bubble? Okay. 6 and 2? Swap. 6 and 4? Swap. 6 and 7? No. See, I fixed some bubbles, but what I can really guarantee is that this next maximum is going to end up where it belongs. Because this one, from here on, is going to bubble up with everybody. 7-1, swap. 7-5, swap. 7-8, good. At this point, I think in bubbles, I can say I've done 2 rounds. Those last 2 guys are good. Because I got the first maximum, first time, second maximum, right? But I still have to go from the beginning. 3 and 2, bubble, swap. 3 and 4, bubble, no. 4 and 6, no. 1 and 6, yes. 6 and 5, yes. I could keep checking those, but I already know 7 and 8 are in the right spot, right? But if I would check them, it won't be significant amount of extra time. From beginning. 2, 3, good. 3, 4, good. 1, 4, you gotta swap all the time. 4 and 5, good. 5 and 6, 6 and 7, 7, 8, right? So I go again from the beginning. 2 and 3, good. 1 and 3, swap. Everything else to check out. 3, 4, 5, 6, 7, 8, right? Again, 1 and 2 here, swap. I'll check all the others. There's no bubble left. I still have to go one more time. Bubble sort, you gotta go one time to make sure there's no bubbles. So like kind of, I assume there's no bubbles right now, but 1, 2, good, 2, 3, 3, 4, 5, 5, 5, 6, so on and so forth. If I found no bubble, can I guarantee this array is sorted? There's no bubble. So then I can stop. I say, this round I found no bubble, therefore it's sorted. Easy peasy, right? Bubble sort. Again, A, B, C, D, F, G. Sorry, guys. Let's do another one, huh? So we done insertion sort, bubble sort. Yeah, that's it. Well, let's do merge sort then. Everybody knows, people have heard of merge sort, right? Merge sort doesn't look at any value. Everybody closes the thing. Just splits in half. Say, okay, half is here, right? 4 and 4. Split, 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 good. Right? Right? And then says, okay, I have 2 halves now, right? I'm going to sort this one first, and then that one. Or if I have 2 computers, I can set that one to one computer and this one to another computer, because they're going to sort independent of each other. I'm not combining them at all. I'm just saying I have 2 arrays now, sort this one, sort that one. So how do I sort this array with merge sort? Split. So let's split. I still didn't look at any value, by the way. I see I didn't open the folders. And then either after or in the same time, I could sort this as a split. Okay? So now I'm going, I have to sort this, and then figure it out together. And then I have to sort this and that, and then figure it out together. Right? So let's sort this one. How do we sort in merge sort? Split. Split. Split, split, split. But I keep track of who was in what group. I know those 2 were a group, those 2 were a group, and then 4 were a bigger group. I have to keep track of this grouping structure. So now, if she's only one person in a group, that's sorted, right? I don't have to do nothing. One element, it's sorted. This is sorted. All I have to do now is figure out how to, since this is sorted, how to put it together back in their group. So I look at their values, 6 and 3. When to sort them properly, they have to reverse, right? So now this group is sorted. The same thing here, I look at this group. Each individual is sorted. So 7, 2, when I do the merging procedure, I have to somehow figure out, okay, you guys go in a different order, 2, 7. Then here are 4 and 8. They sorted each of them, but when I put it together back to the group they were, I have to check 4 versus 8, the correct order. So I leave them like that. And finally 1 and 5, that's the correct order. Now I go back higher in the hierarchy to a bigger group. I look at this group. This is a sorted group now. This is a sorted group now, correct? I sort them already. But I have to find a way to kind of interleave them properly, right? I can't just say 3, 6, 2, 7, nor I can just sort them 2, 7 first and then 3, 6. I have to do what's called merging or interleaving. Interleaving would be a much better technical name because it's really interleaving. Anybody knows how can I do that? Interleaving? Yes.
Compare the first two elements of each
First
of
2,
your list.
2 and 3. Who goes first?
The two.
2. The 2 comes up in front. He's putting in another array. Then
And you
I'm
compare
at 3, then at 7. Who goes first?
three.
3 comes up. Then between 6 and 7? 6. Between now 7 goes here, right? So I kind of interleave them. I gotta be careful to go F to each element exactly once because I want this to be a linear procedure. I have to take advantage of the fact that the groups were sorted. Because if they're not sorted, it can't possibly be a linear procedure.
At this point, does it have to be an array or would it be better done as a list?
Let's see. That's a good question. Like for insertion sort, we already discussed the list versus array. List will give you some benefit, but some problems. Array will give you a different benefit, but other problems, right? He's asking, is this better to do in a list or an array? Clearly in an array, the way I did it, when you guys step forward, that's a new array. So it's not the two that are combined. I still have those two, but I'm putting the data in a new array. Let's do the same thing here. These guys are group sorted. This group is sorted. I want to do the same exact thing. Start with the first one. 1 and 4. 1 goes first. Now 4 and 5. 4 goes first. Then between 5 and 8, 5 goes first, and 8 goes here. Now I got the two groups sorted. I go up one level where I combine those groups. So I start from the beginning, 2 and 1. Who goes first? 1 goes first. Then I'm still at 2 versus 4. Every time he goes first, my index moves to the next guy in that group, right? He was the first, but he got promoted. I got 4 now versus 2. That 2 is still there. My pointer in the first group is still at 2. So between 2 and 4, which one goes first? The 2. He goes here. But then I move to in that group, I move to the next element. Between 3 and 4, 3 goes here. And I move to the 6 there. Between 6 and 4, 4 goes first. So now I have the 5 and the 6. 5 goes first. Between 8 and the 6, 6 goes first. And now between 7 and 8, 7 goes first. And finally the 8. Did it work? Very good. Merge sort is a little tricky to manage the groups. You have to remember the group's hierarchy when you go down, but also you have to remember when you go up to be careful not to break that this group was from here, now merge it with that group that was its pair group. It doesn't work if you do it, across the groups. One more time, guys. Let's do the selection sort. A, B, C, D, F, G. Everybody got merge sort? Same order, right? So here's how selection sort works. It's the simplest one. I don't know why we put it at the end. It's the simplest one. It says you want increasing order, find the minimum. Let's look at everybody. Where's the minimum? How long is that, a linear search or a binary search? Or what, or a chunk search? What kind of search is that? I'm looking for the minimum. Why linear? It's not sorted, right? So I'm looking for a value, it's a linear search, I find the minimum. How many? It's theta of n, right? I find the minimum, I take him, put him here, and he's done. He's the first, that's it. Then I repeat, where's the minimum now? That's the 2. How long is that gonna take? It's still a linear search, right? Because these guys are not sorted. So I go one by one, find the minimum, 2, promote here. Again, find the minimum, 3, that's still a linear search. Every one of finding this minimum is a linear search. The only trick is, it's not in the n elements. If I found 2 minimums already, how many elements I have left? So this linear search is not in n, it's in n minus 2. Okay, 3 goes here. The actual act of picking the minimum and copy it in the output array, that's O of 1, right? I just take, once I know what the minimum is, I just put it here in the front. That's constant time operation. next minimum 4, linear search in 5 elements, 4, linear search again 5, goes in here, linear search in 3 elements now, 6, 7, 8, 6 goes in here, 2 elements, 7 goes in here, and 8. That's selection sort. Repeatedly finding the minimum, putting it in the output. That's never going to change. Once he got the first time in the output, I didn't touch that value anymore. Once I declared that's the minimum, putting as the first element of the output, I never have to worry about this value again. Because that's globally fixed now. I'm not going to change my mind. The same thing with second minimum. Once the second minimum became the second minimum, I never even looked at that value anymore. Every other value got put into output array one after the other, but those two I didn't check again to say verify that they're indeed minimum, nothing like that. Because they were global minimums at their time. Global minimum in 8, global minimum 7, so on. Hands up, who's with me? Good. Thank you guys. No, we need it for other sections. But you guys can make this very, very interesting. So, what did we just do? Did we finish sorting already?
It's in order to bring those, so you have to walk
We finished sorting, right? Well, let's do a little bit of analysis of that. Okay, we kind of done basic sorting because we had the first 4 methods. Did you guys write anything down, by the way? Yeah, I mean, how are you going to know at home which was one bubble sort? In the video? Yeah, I think we have to write some notes of some kind, right, to have them for later on. How about merge sort? Let's discuss each one of those 4, the first ones, a little bit, with some details. So merge sorts. Here's what we want, like physically, to happen in the memory. 6, 3, 7, 2, 4, 8, 1, 5. Those are the same values you've seen, exactly in that order, A, B, C, D, and D, H. So how does merge sort works again? We split first. We don't look at the values really. It's an array. We split, right? So when we split, we get 6, 3, 7, 2, 4, 8, 1, 5. And now we go on each side, we split again. 6, 3, 7, 2, split. 4, 8, 1, 5, split. And then again we split. 6, 3, 7, 2. But this is a bigger split in here. And this is a very big split in here. 4, 8, 1, 5. Now that we got individual, of course that I pick a number 8 of elements. Makes it very easy to do those splits. If you have 10 or 11 elements, you're going to have multiple layers here. Some group will end at this layer, but some group will keep splitting because not all groups will end up after 3 splits. But that's okay. And then that's the splitting part. And once I'm down to the 1 element, I do the merging part. How do I do merge? 6, 3. When I merge them, become 3, 6. 7, 2. When I merge them, becomes 7, 2, 2, 7. 4, 8. And 1, 5. But I keep going, right? The merging goes now to the previous groups. 3, 6, 2, 7. How do I merge this again? I start with 3 and 2. Which one is the smallest? 2. Now that I did the 2, I'm advancing to the next element. So I still have 3. I'm at 3 and 7. Between 3 and 7, 3. I advance the dot at 6. Now between 6 and 7, 6. This is done, so that's got to be 7. In here I do 4 and 1. Which one's the smallest between 4 and 1? 1. Once I put 1, I advance my pointer to the next value in that group, 5. Between 4 and 5, that's 4. I advance to 8 between 8 and 5. That's 5. And now, of course, the 8 is the last one. I do the same thing. I move to the higher level of grouping. 2 and 1, I start from the beginning. 2 and 1, which one is the smallest? 1. I advance this pointer here to the next value because 1 got copied. 2 and 4. 2. I advance this advancing the pointer is the critical step in merging. Once I put the 2 here, the pointer got to 3. Between 3 and 4. Wait a minute. This 3 was never compared with the 1, right? I compared the 1 with the 2. I put the 1 up. And then I move the pointer to 4. That means no other element will be compared with the 1. Is this a guaranteed thing to work? Why? Because everything was already sorted. This will not work if those two groups were not already sorted. You cannot say, okay, you put the 1. You just compare 1 with 2, and I decided to put the 1 up. That works because this is sorted. If 1 is smaller than this 2, it will be smaller than everybody here. But if this was a random order, I couldn't have decided in one comparison, 1 is the one to go first. Yes?
What's the name of the thing that you did that it compares the first one of each thing and then it pulls it out? What is that specific thing?
That's called the merging procedure, which is not the merge sort.
You mentioned it was called like mice.
Interleaving. That would be a better name for it because when you say merge, you know, two rivers merge. They don't merge in order, but interleaving is a very specific thing in combinatorics that means in order. Okay, so everybody sees that if I compare 3 with 4 right now, and 3 wins, I can safely put 3 here. I don't have to worry about the other values in either array. Because at this point, smaller than 4 means smaller than these guys, and it's already smaller than the other guys in its own group. So between 3 and 4, 3 is already known to be smaller than this. If it's smaller than 4, it's also smaller than the rest of the group. Therefore, 3 can go first. And once it goes, I can advance to the 6, right? 4 and 6. Again, 4 wins with 6. That means it's going to beat the other guys in this group. 4 already won with these 5 and 8 pieces sorted, so I can put it there. Advance to 5, 5 and 6. 5. Advance to 8, 8 and 6. 6. Advance this one to 7, 7 and 8. 7. Now, of course, it's only 1 left. I could, whatever's left in here, I can just copy it in there because these guys are in order already. That's more suitable. If I'm to write this recursively, I describe a physical mechanism. This is what actually happens in computer memory, not how to pseudocode this procedure. How can I do this merge sort of an array from B to E? I want to sort it. I pick the middle, right? B plus E by 2. That's where I split it in half. Now I have to do merge sort of the first half, that is from B to M, and then merge sort, say that's an array B, that's an array C. Merge sort A from M plus 1 to E, right? So I took my array, I split it at M, I say sort the first half, not this array, the input array here. Sort the first half, that's what I did, right? Eventually I've got this half sorted, 2, 3, 6, 7, and then sort the other half, M plus 1 to E. And now that B and C are sorted, that was those big groups, 2, 3, 6, 7, and 1, 4, 5, 8. I have to merge them. That is not a recursive call. These are recursive calls. This, merge B and C into an array D, and then return D. This procedure is not a recursive procedure. It's just a black box. Give me 2 sorted array, I'm gonna interleave them. I like that name a lot, interleave. Problem is just me. If you say anybody interleave, nobody knows what you're going to talk about. So you have to call it merge sort. Everybody knows that name, merge sort. But the real mathematical thing is actually interleaving the values. So we need to have a separate pseudocode for how this procedure works, right? Because it clearly, we know what we want to do. We have to write that code somewhere. So that's an exercise for you guys. Merge two arrays. Let me start it for you. I have to start with I equal 1, j equal 1. That's starting B and C. They already sorted. We don't have to verify that. I start with what? And I say if B of I is smaller than C of j, right? Those are my pointers, my indices. Then I have to do something. I have to decide which element gets promoted to the output array. If it's element from B, what do I have to do? If the B1 is promoted, so B of I gets to the output. D of the counter here gets to be B to the I. What else I have to do? If I decided to promote B, how do I advance in the B array? I equal I plus 1. What if not? Who I promote in the output? I promote the other value, C of j. Right? One of them has to be smaller. Which one is smaller? I promote it into the output. This is my output. And how do I advance in the C array? J equal j plus 1. Of course, this counter has to be increased. I start with counter equal 0. And at every time I go in here, I have to do C equals C plus 1. And there's some things that you have to finish in this procedure. How long is this going to take? If I get two array B and C's, roughly of the same size, how long is it going to take to produce the interleaved or merged D array? Linear time. It's easy to see that when I advance that dot in both arrays, no matter who gets advanced, every element had a dot how many times? Did the dot came back ever? So every element had a dot once. That's what's going to make a linear time for only the interleaving merging procedure. But now that I'm looking at this, I want to measure the runtime. Let's call the runtime, this is n elements in here. We usually use the letter T for runtime. It's very popular, all the books does it. T for n is the runtime for an array of size n. Looking at this procedure, what happened here? How long this takes? This line. Constant time. So I'm gonna kind of read the pseudocode and see the whole thing, how long it takes. This is constant, how long this takes? If merge sort for n is T of n, how much is merge sort for, how much is in here? Half of the array, right? So how can I write this in here? T of 1 over 2. That is sorting just half of it. I don't know how much T of n is, but I'm just calling a generic function T of n is how long it's going to take for n. Then this must be how long it takes for a half, because it's the same procedure, just for half of the array. Does that make sense?
Because it's recursive, doesn't it? Like, so you have linear time. So linear from a bunch of times is still linear time.
Depends how many times you use it, right? So the linear time that I described was just this. When I say the runtime for merge is linear, I only mean this part in here. I didn't attack the other ones. The problem with recursive calls is I want to measure the runtime of this. I have to have some runtime for this. That's where the recursion is coming from. I'm going to say generically T of n is the merge sort to sort any n elements. So the sorting of n by 2 elements is going to be T of n by 2. which I still don't know how much it is. I don't know, right? Everybody's with me here. I'm not saying I know how much T of n by 2 is. I'm saying, by definition, T of n by 2 will be the time to sort n by 2 elements. I have to find out how much it is. How about sorting the right half of the array? Same, because it's still sorting n by 2. And the merging part takes, which already said that, it takes linear time. So I have a recursive equation that I have to solve here. I have to figure out what kind of function has this property. It's kind of linear. The constant really doesn't matter, right? Constant plus linear is still linear. So it's a linear plus, I'm going to say this is 2t of n by 2 plus linear. 2t of n by 2 plus linear. Because constant plus linear is just linear. I'll have to figure out a way to solve this equation to say, what is this a logarithm? Is logarithm behaves like this? Logarithm of n is 2 logarithms of n by 2 plus n? No. N squared behave like this? Is n squared 2 times n by 2 squared plus n? Maybe. I don't know. Maybe n cubed, maybe 2 to the n. We don't know. But solving a recursive equation comes down to what mathematical function has this kind of behavior. In asymptote, we're not going to worry about the exact function. We're going to worry is like log n, or it's like n squared, or maybe it's n cubed, or maybe it's exponential 2 to the n. We'll see. That comes next week, how to solve recursive equations. Are we happy with merge sort? Hands up who's with me on merge sort. Very good. Now here's an exercise for you. I would like to implement merge sort. What I mean by implement is have this behavior in computer memory. If somebody can really take a look at the computer memory, I really want it split into groups and merging and all that, but not recursively, without a recursive call. Remember how we do binary search with recursive calls and without recursive calls? Can you implement this in a while loop of some kind, in a for loop that doesn't call itself, but rather in the next iteration of the loop does the halves and the quarter and so on and so forth and brings it back, just like with the binary search. So I want the same exact behavior in terms of the groups, the splits, and the merges, just not in the pseudocode with a recursive call. Since we're here, I want to make a small parenthesis. Binary search, array B to E, I'm looking for value V. What was the recursive version of binary search? M was B plus C by 2, right? If A of M is equal V, done. If A of M, recursive version, bigger than V, what do I have to do? Call binary search of. If the value is smaller than the middle, what do I have to do? B to, say M. I know M is already checked, like we go to M minus 1, but just to be easier. It doesn't hurt to just check M again. I have to go here on the right side, right? What's the right side? M to E. And then I have to say something, at some point there's a condition here that, you know, if B and E are too close together, I shouldn't do this. I want to do the same analysis like in here for the runtime. The same kind of count. Let's call T of n the size of the array. So this is the runtime, how long it's going to take to do binary search in an array of size n. Look at the pseudocode. Condition is theta of 1, right? That condition probably should be checked in constant time. Like if B is close to E or equal with E, done. This will take constant time. This will take constant time. Right? If that done. This here will take what? Tn over 2, because by definition T of n is the binary search time of n elements. This is a binary search of n by 2 elements. So this will be of T of n by 2. How about this? How long is this going to take? T of n by 2? Do I say here plus T of n by 2 like that? Why not?
Only one of those can happen.
Only one of them is going to happen. How about in here? Both happen. So this is that, how long that takes, plus how long that takes. In here, either one of them will be executed. This one gets executed all the time. That's a constant time operation. But between those two, would I ever execute both of them? No. This is an absolute critical part when you read pseudocode for runtime. Even though it looks like naively speaking, you have so much to do here, so much to do, so much to do here. Out of those two, only one happens. Hands up, who's with me? Good. So I don't need another T of n by 2. This is either left or right. And then nothing else, right? There's nothing going on here. So what's this definition? T of this recursion here is like constant time plus T of n by 2. Again, if I wouldn't know the runtime for binary search, do we? Because we analyzed the other version, the one with the iterations, how many iterations it takes until it goes down, remember? But suppose I wouldn't know. Now I have the problem, what function behaves like this? Is it an n function, n log n, n square, square root of n? Which function mathematically has this kind of behavior? But we already know that function, right? Because we know the runtime of binary search. How much is it? We know this is log n. But for sanity, we can verify. Is the logarithm behaving like this? Logarithm of n is a constant plus the logarithm of n by 2? Check. Is logarithm of n a constant plus logarithm of n by 2 in general? Is that the property of the logarithm, that the logarithm of n is the logarithm of n over 2 plus a constant? What's the constant? How much is log of n divided by 2? Do we remember that? Log of a divided by b? So how much is log of n by 2? Log of n minus log of 2. Log of 2 is how much? 1, because this is log base 2. So I need a constant here to compensate for that minus 1. The constant is 1. So it's a good thing to verify once you get the logarithm. Like in this case, we knew it's logarithm. Say, okay, we know it's logarithm, but let's just check. Does logarithm has this kind of property that logarithm of n is logarithm of n by 2 plus a constant? It is. Just put that constant 1 and you get logarithm of n is 1 plus logarithm of n over 2. Again, why is that? Logarithm of n minus logarithm of 2. Logarithm of 2 is 1. Cancels out, remains to log n. So that's merge sort. We talked about bubble sort. Let me see if we get there. Let's talk a little bit about bubble sort. Actually, somebody in the back asked a question here. What's up with the merge sort? Does it have a list or an array? Was that the question?
Yes.
I don't remember what's for merge sort, but I do think what's for merge sort.
Yeah, it was the merge sort because as you bring them back together, it seems like it might be better to do this stuff.
Right, except I still have this step in merge sort. If I put things in a list, I have to be careful whether, when I do this operation, can I do it on lists? can I compute the middle? Middle maybe I can compute, but can I access a list just from the beginning to the half? Is there a way to say, just operate on this list from the beginning of the list to half of it? I don't think that's possible. But maybe he means, no. When you go down, you can use arrays.
Yeah.
Only when you come back up, merge things together, use lists. But then it requires some duplication of the data. I have to have some array when I go in and some list when I come back. I think clearly doesn't work just with lists. Merging might be easier to do. I think it's still linear time because it's asymptotically maybe the same, but in practice different number of steps. Since when I'm computing this output array, I'm picking whatever value is smaller, and I know already where I'm putting it. I'm putting it in position C of the array, which is a counter that increases, so I don't have to look for that spot. Bubble sort. In bubble sort, what's the runtime? So remember how bubble sort works? Let's have that example again. 6, 3, 7, 2, 4, 8, 1, 5. Can you guys tell me what are the bubbles here? That's an analysis, not part of the algorithm. Is 6 is bubble with who? Is 6, 3 a bubble?
Yes. Yeah.
6, 2, 6, 4, 6, 1, 6, 5. Those are all the bubbles with 6. How about with 3? What bubbles start with 3? 3, 2, and 3, 1. 7 has bubbles? 7, 2. It's everything that's after it but smaller than it, right? 7, 2, 7, 4, 7, 1, 7, 5, right? How about 2? 2 has any bubbles? 4? It's just 4, 1. How about 8? And 1 has any bubbles? No. So those are the bubbles, right? Even without paying exact attention to when exactly bubbles gets flipped, bubble sort, since it just flips bubbles, eventually have to flip all these bubbles, right? Independent of the order which bubbles gets flipped first, to be correct at the end, those bubbles have to be fixed. Otherwise, it won't be correct. So pretty much, I think bubble sort, without math rigorosity, depends on how many bubbles are there, right? The more bubbles are there, the more flipping they have to do. I'm not saying I know in how many runs. Bubble sort runs in runs. The first run, fix some bubbles. Go again from the beginning, fix more bubbles. And go again, fix more bubbles until there's no bubbles to be found. I can't tell how many runs it's going to do, but I know it's going to have to fix all these bubbles. Maybe somehow a lot of bubbles can be fixed in the first run, and then I have less bubbles for the second run. I don't know. But what's the worst case? How can you possibly get an array which has a lot of bubbles?
It's an opposite order.
Backwards. So if this input is a of n to n, what will be the backwards? How this array has to be sorted to be exactly backwards? A of n has to be the biggest, sorry, the smallest. And A of n has to be the biggest, right? Is that the worst case? Is that the one with the maximum amount of bubbles? Are we sure? Is there a way to come up with n elements with more bubbles than this one? No, because every pair is a bubble here. Everything is in the wrong order. Right? So how many bubbles are in this worst case? It's the same as the number of pairs, right? Because every pair is a bubble. So how many pairs are here? I have n elements. How many pairs are there? Counting 101. And choose 2. So how many bubbles this algorithm will have to fix? And choose 2 bubbles, right? Only fixing those bubbles, it's n times, we know the formula, right? asymptotically this is what?
Insert.
N squared? Because it's n squared times the coefficient. It doesn't matter the other n's that are in there. The dominant degree of this polynomial is n squared. And it doesn't matter the coefficient, whether it's 1/2 or 1/3 or 3 or 100, it's still theta of n squared, because it's between two n squared functions. Hands up, who's with me? Are we clear on why this is n squared? It's n squared, some other things, the n squared is going to dominate that theta bound. So worst case, it's easy, n squared.
If it was a worst case, would it be big O of n squared and not theta? Because it's the upper bound.
That's not what O and theta mean.
Oh.
So O, theta, and the other one, omega, does not refer to worst, average, or best case. They only refer to our ability to estimate this function. If I can put this into two n squared functions on both sides, this is definitely the worst case, right? If I can write it smaller than some constant of r squared and bigger than some other constant of r squared, of course different constants, then that's a theta thing, because I can bound it left and right. It doesn't matter whether it was worst case analysis or runtime, recursive analysis or average or amortized analysis, whatever. Whatever it comes from, theta, O, or omega, the three symbols discussed last time, have to do with how well can you estimate this function. Do we believe we got the upper bound and the lower bound? What constant do I need here to make it work? To be smaller than n squared? 1. If I put C2 equal 1, this is smaller than n squared. Everybody can see that. What constant do I need here? I need something to make this always bigger than this constant times n squared. What constant can I put here? Can I put a half? Huh? No, because that will be n squared a half. This is less than n squared of a half. A little bit less. What can I put? 1/3? If I put 1/3, this is going to work. 1/3 of n squared is smaller than this. So I have bounds both ways. If I have bounds both ways, what kind of approximation asymptotic is that? Theta. It doesn't matter whether it was a worst case analysis, expected analysis, average analysis. It only matters with our ability to declare the behavior of this function. Since we can bound it both ways, it's theta. Suppose it's a very complicated function that we can only bound this way. We say it's smaller than n squared, but we don't know what's bigger than. We don't know enough math. Then we say O of n squared. It has to do with whether we can get both bounds or not. How about the best case in bubble sort? Can I be lucky in bubble sort? What would that case be?
It's already sorted.
It's already sorted. How many runs I have to do? One run. How many bubbles I have to fix? 0. How long would that take?
And
It's sorted already, right? Input. That will be, can I declare a theta bound for that? Or just an upper bound, or just a lower bound? That case would sort it. That's a best case analysis. If I have to go once through it to look for bubbles, I find no bubbles. Then looking once through it, how long is going to take? But is it a theta of n? At least n, at most n, or just about n? Just about n, right? Because you have to go through the array and nothing else. So you're going to take n steps, not more, not less. That's why it's a theta bound. How about on average? Yes.
There are n elements, aren't there? N minus 1.
If you make them consecutive like that, just pair with a neighbor, yes. But you see my bubbles here? 6, it's a bubble with 2 and with 1, even far away.
Yeah.
Now, what you're pointing out correctly is that 6 doesn't get swapped with 2 in bubble sort. It only gets swapped with the neighbors. My point is, eventually it's going to have to be swapped to 3, right? You're going to have to swap it somehow in bubble sort. At some point, you're going to have to swap 2 with 6. It's true that bubble sort only swaps the bubbles which are next to each other, but by different, 3 will have to swap, 2 will have to swap. At some point, 6 and 2 will have to be swapped. Right, in the best case, there are n minus 1, but n minus 1 is theta of n, right? Is n minus 1 constant of n, and another constant of n? Sorry, I put the C2 in here, C1 in here. What will the constants that make this work? What constant do I need here? 1. N is bigger than n minus 1. What constant do I need here? 0 is not allowed for constants. Is there a constant that makes that times n smaller than n minus 1?
Anything small.
Yeah, like 2/3 or 1/3. 1/3 of n is going to be smaller than n minus 1. It may be true that it doesn't happen for n equal 1. I think that's his point, that for n equal 1 that doesn't work. But remember, we don't care about the beginnings. N equal 1, 2, 3 doesn't matter. We care about asymptotic behavior. If I put here 1/2, half of n, is it going to be smaller than n minus 1 as n goes large? Yeah. How about the average case? What does the average even mean? Oh, here's the definition of average, very naive. I run the thing on an array of n inputs, n equal 100, a billion times. I measure the clock, how long does it take? And I make an average. Is that what average means here? I run an array of n inputs, whatever array somebody gives me, a billion times. And then I measure how long does it take each single time as a function of the array size, n equal 100. And then I make an average, and I say that's my average case.
Could we use like expected?
We can use expectation. But my point is, what's wrong with my experiment?
It has to be different arrays, just it can't be the same one. It take the same amount of time.
Right. I wouldn't say necessarily different. I think you're correct, but the issue is if I use practical arrays, suppose I'm a machine that sorts students for a university. And I keep sorting things all the time, or sort money for a bank, or sort, Is it possible that those input arrays are not truly random? They somehow biased. Most students have been mostly sorted most of the time. So even if I do it a billion times, I'm only doing a billion times with arrays that are not quite random. They are biased towards being less sorted or more sorted. So what average means is average runtime is the expected, or say average, where A is a random array of size n. That's a little difficult to do. We need to set up the shop like we did for collisions. Hey, what this average random means? Every two values have a 50-50 chance of being in that order or the other order. So if I'm to not do it rigorously, but do it intuitively, how many bubbles are here? We already said that. Total number of bubbles n by 2. Now suppose like in expectation I declare a random variable for each bubble. I would say expected, this thing will be expected of x1 sum over xij, where xij is a random variable. It's saying is 1 if ij is a bubble, 0 if not. Am I correct to say that expected number of bubbles, it's like in collisions in a hash, right? This is all the possible bubbles, each one of them is 0, 1. So the expected number of bubbles will be the sum of the expectations. How many of those are there? N choose 2 variables, just like in the collisions, we have this. What's the expected of a bubble? If I pick a random I and j, what's the chance that they're in the right order versus the wrong order? 1/2, right? Because random means every two elements have equal chance of being this way or that way. Now, how much is this in terms of asymptote? It's still n squared. It's a smaller exact number, but it's smaller by a constant, in asymptote, it doesn't matter the constant, it's still n squared. So the average case of bubble sort is the same as the worst case. It doesn't buy me anything, good. But it's true that there's a best case. You can be really lucky with bubble sort and not have to sort. Your nearly sorted array problem have a lot to do with this.
In our best case, we consider heresies, but in our average case, we consider
I'm only doing this a little bit non-rigorous when I say if there's that many bubbles, kind of that's how long it's going to take, independent of how many runs you drew to the array. I'm saying the effort of bubble sort overall seems to be with how many bubbles have to be swapped. I'm cheating you there because that's a theorem that needs proof, right? Implicitly, I'm saying the bubble sort runtime depends on how many bubbles are. But what he's saying, wait a minute, you have to go once, maybe you only fix 2 bubbles, you have to go again. Is it really going to be how many bubbles are there? Doesn't matter where those bubbles are. I'm saying, trust me. I really don't want to say that, but I'm saying, trust me. The more bubbles you have, the more this is going to take. And on average, it's only half. That you can see. If every bubble is 50-50, the expected number of bubbles is just half of the total bubbles. Now, insertion sort. That's the most important one, insertion sort. Okay, so here's back to our array, insertion sort. Let's do a little bit of analysis. Our array, the one that people demoed in here, was 6, 3, 7, 2, 4, 8, 1, 5. That's our array. So how insertion sort starts? The first guy is the 6. Nothing to do for the first. Then the next element is 6, 3. Does it mean I'm looking for 3 to be swapped inside, right? Is 6, 3 in the correct spot? So let me say 6, then 6, 3. Do I need to swap 3 in here? Yes. So it's going to be 3, 6. Then I do 3, 6. 3, 6 is what I have already. I bring down the next element, 7. Is 7, I compare 7 with 6, is that good? Good. So I move on, 3, 6, 7, that's what I have so far. I bring the 2 down here. Do I need to swap 2 inside or not?
Yes.
Do I need to swap 2 over the 7? That's going to be 3, 6, 2, 7. Do I need to swap 2 over the 6?
Yes.
That's going to be 3, 6, 3, 2, 6, 7. Do I need to swap 2 over the 3?
Yes.
That's 2, 3, 6, 7. Everybody understand this? The way insertion works to bring the 2 to the right spot, I drag him one by one until I get to that right spot. Even though I could have done binary search and figure out exactly the right spot is between 3 and 6. I don't do that. I just drag it little by little. Now that I have 3, 6, 7, 2, 2, 3, 6, 7. From here. That's what I have so far. So far, I have it already sorted. I only need to worry about the next element, which is the 4. Do I need to bring 4 inside? That's going to be 2, 3, 6, 4, 7. Do I need to move the 4? Yes. 2, 3, 4, 6, 7. Now, when I do this with the 4 is my troublemaker here. Do I need to worry about the order of the other elements? No, because they're sorted already. Their relative order doesn't change. Just the 4 has to be placed, inserted somewhere in between them. Ends up with me here. Insertion sort is the simplest one, but also the most useful one in computer science. As far as the basic sorting goes, there will be some more useful ones, but they're more complicated. What's the next guy? 2, 3, 4, 6, 7, that's what I have. I bring down the 8. Do I need to swap this 8? No. 2, 3, 4, 6, 7, 8. What's the next one? 1. These have to be swapped. 2, 3, 4, 6, 7, 1, 8. Swap again, right? I only look at the left element and I say, maybe I need to swap it, maybe swap it. That's going to happen a bunch of times until 1 has to go where? All the way to the front. 2, 3, 4, 6, 7, 8. And finally, 1, 2, 3, 4, 6, 7, 8. I add the 5. That's the last element. 5. Do I have to swap 5 in here? 1, 2, 3, 4, 6, 7, 5, 8. Swap it again. 1, 2, 3, 4, 6, 5, 7, 8. Swap it again. 1, 2, 3, 4, 5, 6, 7, 8. How do I know that's the correct spot? How do I know to stop it? I check 5 against the left element, the 4, and it's good. Just the same way I stop here, 4 versus 3, just the same way I stop here. 2 was at the end, I didn't need to check anything. So that's how insertion sort works. The runtime of insertion sort, it's really the runtime of inserting the first element plus the runtime of inserting the second element plus the runtime of inserting third element plus the runtime of inserting the nth element, right? Because those things happen in a sequence one after the other. The first element gets put, then the second element gets put, inserted. Once that's done, I have 6, 3, I'm good with that. Then the third element gets inserted. So it's really a sequence of inserting one by one all these elements. And this is n steps in here. First, second, third, up to n. Worst case. How long is this one going to take? This one takes nothing, because you don't do anything in terms of comparisons. I'm talking about runtime as the number of swaps or comparisons. All these algorithms require a little bit of kitchen, I, j, I plus 1, so on and so forth. We're not counting those. Let's just count how many times we have to swap, like in bubble sort, how many times there's a bubble. The first one does not require any swapping, right? Because it's just the first element. There's nothing to compare with. Worst case, the second one. How many times I have to move it to the left? 1 time. Second, the third time, how many times? In the worst case. Then the fourth time, once I have 3 elements already, if I put a fourth one, worst case, how many swaps I have to do? And the last one, when I have n minus 1 elements, 1 up to n minus 1 swaps, I put the last one. How many times I have to swap it in the worst case? N minus 1. By the way, what's the worst case? Is it the same worst case like in bubble sort? Is that the worst case, the one that's exactly backwards? That's the one, because everybody has to be dragged all the way to the front, right? The same exact worst case. Anybody knows how to sum up these things? That's a series we're going to study on Tuesday, right? How to sum up things. But really quick, right? Like, can anybody, yeah? No, I know, but how do you get there? That's magic, right? Yes.
You sum up the first and the last one, which is n minus 1.
Uh-huh. So if I sum the first and last, how much is that?
It's n minus 1.
It's
like,
Let's keep the 0, huh?
Oh, okay. So it's just n.
N, and
And the
then
second
the
one,
one
the
here,
second
n minus 2 with a 2, n, and n minus 3 with a 3, n. So how many of those pairs are there?
N over 2.
So it's n over 2 times n. Roughly. Because I don't know if you get exactly n over 2 pairs, to be honest with you. Is it possible you don't get n over 2 pairs? Maybe you get n over 2 minus 1 pairs? Because I skipped the 0, I don't know. You guys check how many pairs are, but everybody sees the principle here. If I do first and last n minus 2 with 2, another n minus 3 with 3, another n, I have to count how many pairs I have. That's roughly half of them times n each. Is that, how much is this? Asymptotic notation.
N squared.
Yes, question. There was a question in the back?
Oh, yeah, I was just gonna say, I think it's n over 2 minus 1/2.
Right. But it wouldn't matter if it's n of 2 minus 1 in terms of asymptote. That will matter in terms of the exact number, but as far as the asymptote goes, that will still be n squared. Every polynomial that's dominated by the n squared with any coefficient that's positive will be theta of n squared. Everybody sees that if I have a -1 here or minus 0.5, the polynomial is still n squared times something. Hands up. I really care about insertion sort. You know, bubble sort is fine. There'll be an exam question. And, no, I'm kidding. But insertion sort, you have to absolutely know. There are many things based on insertion sort.
Can you do this with letters too?
Yeah. Because I need to be able to swap things. If the two letters, I know which one's in the right order or wrong order. AB is the correct order, but BA is the wrong order. So the insertion sort, bubble sort will look exactly the same. It's just that swapping numbers, I swap letters. Or anything that's orderable. Colors, if you define colors by, you know, this is first, then that second, then that third, I can swap the colors. As long as there's an order, I can swap things. How about the best case? How many swaps I have to do in the best case? This is always 0 because I have to do nothing. How many swaps I have to do here?
0, 0, 0, 0.
I have to do no swaps at all. But I still have to go for each round, right? I have to check no swaps, no swaps, no swaps. I have to go for every element, put it there, figure out, okay, you put it here, you don't need to swap it. But I do have to go through each element once, right, to check there's no swaps. It's 0 swaps, but still theta of n, right? Because I have to go through every single element and check if it needs a swap or not. That makes sense? That even though I don't do any swaps, I still have to check every element. How about the average case? Can I kind of do this fancy thing with since the runtime can be split into n runtimes, can I say the expected value of the runtime is the expected value of inserting the first plus expected value of inserting the second? Because the expectation will always distribute over a sum. Plus the expected value of inserting the last one, right? Now, what's the expected value for the first? 0 swaps. It's still 0. In here, when I have 1 swap, that's the worst case. But what's the probability of needing a swap? If I look at 2 elements, what's the chance that they have to be swapped? 50%, right? So every one of these will be, there's 1 possible swaps, but it's 1/2 of that expectation because every swap happens 50% of the time, right? How about in here when there are 3 swaps? There are 3 swaps possible. Each one of them is 50-50, right? So what will be the expected number of swaps I have to do for this guy, for inserting whatever, the 4th element in? 3 times 1/2, right? How about the last one? There's n minus 1 elements already sorted. I have this element here. Every swap is a 50-50. How many swaps do you think I need on average?
Why is the probability that you have 3 swaps for the worst case 1/2? Because each swap is a half itself.
But remember, this is sorted. So I can have a swap with this if I don't have a swap with that, right? Right. So in terms of how many of those are smaller and how many of them are bigger than it determines how many swaps I have. You're right. If I have an unsorted array of n minus 1, number of swaps could be any one of those. But if those are swaps here, the other ones have to be swaps too because they sorted already. Is that what you want to class?
Yeah, I agree with that.
Maybe we should put a question mark in here and come back to it later. I say an average, this is n minus 1 swaps, as in if you have to push this inside, it's a complete random value. On average, you would have to put it half of the way. Would that make more sense? We still need to prove this with random variables. But every one of these pushing inside, you know, I push here the 2, the 4, the 8, on average you'll be pushed halfway because every push is 50-50 and you can stop. So in this case, in the average case, what is the runtime then? If every swap is 50-50? Still n squared? Even though it's a smaller n squared, asymptotically it's n squared nevertheless. I may be wrong about that. I'm thinking now, if I think there is a 50-50 swap with this, there's a 50-50 swap with this, is that a geometrical decrease?
It's not 50-50 with the first element because it's one random and one the maximum of 40. So it's like geometric but not.
I think there's a better way to think about that. I have n-1's element already sorted, fixed. These guys are fixed. And I'm throwing a value at random. At random means there's an equal probability to be here or between those two or between those two or between those two or between those two, right? Randomly means it could be anywhere between these elements, equally likely. Would now be convincing that the average case is kind of in the middle? Right. That I would like to see rigorous proof if we can make it. But I think everybody can see that on average this is still theta of n squared. So we did merge sort, right? For merge sort we don't have a runtime, but we have a recursion. 2 halves plus merging part. Anybody can guess what's this time? If we solve this recursion next week, what's gonna come?
N log n.
N log n. You have a proof? Not yet? All right, maybe. We don't know that. For insertion sort, we have n squared. For bubble sort, we have n squared. But I would like you to know there's a difference between best, worst, and average case. Both of those have average case n squared, worst case n squared, but lucky case, best case what? N, linear, right? How about selection sort? Pick the max, remember how it worked? I don't want to do that on the board. Pick the max, put it first, remember? Pick the next max, put it first. How many steps would that be? The first max takes linear run, n steps. The second max, right? So this is the first max. First max, n. Second max, n minus 1. Third max, n minus 2. Plus 1, right? We already summed this up. Somebody show the procedure for how to sum it up. It's the same series like on the other side. So this is, you see what I mean? That's the same summation like in there. That's a worst case, right? How about the best case for selection sort? I have to pick the minimum, put it on the side. In the best case, how much does it take to find the minimum?
It's the same as usual.
Still n steps to find the minimum, whatever case you have. Still n minus 1, still n minus 2. Best case, exactly the same. So this method, at least, you cannot be lucky with it. No matter what you do, it's going to take n squared. There's no lucky input. But bubble sort and insertion sort, if the array is sorted or almost sorted, they could run much faster. Merge sort, does merge sort have, do you think, a best or average case? Think about the process, split, 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 and then combine, combine, combine. Would that take the same amount of time no matter how the array is sorted or not? I think yes. We'll get to that next week. Yes.
Why would you ever do bubble sort over insertion sort?
When it's nearly sorted, like in the homework. Actually, in that case, they were all the same. But there are some other problems that I wrote for the homework, but they got kicked out. Like, how many bubbles? Can you count the number of bubbles in an array? Or inversions? Not with brute force. Is there a way to count them faster than n squared time? Didn't happen, but I think it's in your recitation paper, the one that you took home. Because that's how it works. Whatever doesn't get in the homework, I put it in the other paper. Now I want to do a discussion about insertion sort. We already talked about list versus array. What's the good part about the list? Again, can anybody remember that from the beginning of the lecture? I'm talking about specifically insertion sort. What can I do very easily in a list? The actual insertion. If I know where, I can put it in constant time. The problem with the list is though, finding the spot. What can I do in an array? Easily. Find the spot. I can do binary search, right? Because the previous stuff, it's already sorted. Finding the position of 4 within those 4 things will take log n time. What's the problem with the array? You can't put things in the middle. You have to move half of the array. But moving half of the array will take linear time. It will take the same time as dragging it inside. This is a critical part of insertion sort. I know how to do the finding a spot in binary search, but for that I need an array. And I know how to do insertion in constant time, but for that I need a list. So is there something that acts like a list, but also like an array sometimes, somehow? Huh? Of course there is, right? There's hashes, there is heaps, there is skip lists. But the one that I want to show you today is called a binary search tree. That's the one we have to do for the honors problem tree. Everybody knows how a tree looks like? Let me do it here. Binary tree has a root, left child, right child, and then this was left, this is left, right, and so on and so forth. In a tree structure, there is a root. And from there is left and right, and everyone can decompose itself. So if I look at a particular node, n, I'm going to call this n.l from left, n.right, and the parent, I'm going to call it n.p from parent. So in a tree node, I have a value. The value is n.b. It's what value I store there. I can store a name, a string, a color, a number, whatever I want. And I have 3 pointers. The left child, which is also a node, the right child, and the parent. And I can manage this structure with arrays, with lists, with hashes, or with pointers in Java. There are many trees implementations. Anybody have seen a tree before? Hands up who've seen a tree. Hands up who worked with a tree of some kind, of any kind in computer science. So you're going to have to do that quickly for the honest problem. But what's the story with the binary search tree? This is a binary tree with a special property. If you look at a node, and you look at the left and the right, not just at this node, but at the whole subtree. This is the subtree on the left side. And this here is the subtree on the right side. In order for this to be a BST, the node value has to be smaller than everything on the right side. All values on right, and has to be bigger than all values on left. So in other words, if the value here is 15, every value in here can, and the whole tree, not just this one, the whole tree has to be at most 15. And everything on the right has to be at least 15. So okay, let's take this array. and make a binary search tree out of it. Where do you think 6 goes? Everybody follows me? I'm reading this array, I'm going to make a binary search tree out of it. 6 goes to the root. I'm reading this tree. Where does 3 go? Left, right? What's the next one? 7, where that goes? Of course I have to manage the tree. It's easy for me to write on the board. You have to go home and manage the, okay, where is the right child of this dude now? Like, depending how you manage your tree, you have to know how do I go to the right child. What's the next value? 2. I compare 6 with 2. I go left. Now I still have the 2. I find some element here. If there will be nothing here, I put a 2 here, but there is a 3. Where do I go from here? Left. Is it clear what I'm doing? I'm looking at the same array. Next one is the 4. How do I go with 4 from 3? Left. But from 3 I go? How about the 8? At 6 I go? Right. And at 7 I go? Right. 8 goes in here. How about 1? Left? 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 How about the 5? Right? Left? Right? Left. Because 5 is smaller than the 6. And here?
Right. Right.
How about I want to keep going, I want to insert the 6.5. Where is the 6.5 going to go?
Right.
6.5 goes right here. Let's mark it square because that's kind of extra. How about I want to insert another 7? Can I do a 7 here? I can. 6 goes to 7. From 7 I have 2 options. Because, see, depending how I declare these inequalities, if this will be not allowed, I'll have to go right. But one of them has to allow equality. In my loose notion here, different books treat this in different ways. I can go either left or right. So let's say we go where?
Right.
Right. I go with that 7 right. From here I go? That's a 7. Now suppose I want to do another 7. 6, 7. Suppose I go left in here. And here I have to go right. I have to do another 7. Again, that matters whether these inequalities allow equality or not. One of them has to have multiple values. How about 6.9? Where that goes?
What if you want to have the
7, 7, 7, 7.
Infinite sevens.
For example, I could have gone the other way. Remember, you have to follow this
Get
inequality.
another 7.
Where would the 6.9 go? Definitely bigger, definitely smaller, and now? Bigger, and now?
Oh. Everybody
sees that everything in the left sub-tree is smaller than the 6, and everything in the right sub-tree is bigger than the 6. But that's not just for the 6. Let's look in here. If you look at this guy, 7, is it true that everything in the left side is not bigger than 7, and everything on the right side is not smaller than 7? That happens for every single node. So then, can you read this tree in a way that's reading in sorted order? Is there a magic procedure to now read this tree in such a way that stuff comes out sorted? Let me give you a hint, and you have to implement this reading recursively. Every structure that looks like this, node, left, right, in what order do you need to read it? Left, node, and the right. But of course, left could be an entire subtree. So if I apply this recursively, I say I want left, node, right. Now left is not a node, it's a subtree. So at the end I do what? Left, node, right. That's a subtree. So I'll end up doing 1, 2, nothing. But after 2 I do the 3, that's the node in the subtree. Then in here I do left, nothing, 4 and 5. I'm done with this subtree. I read the 6 now. I move to the right subtree. In here I have to do left, node, right. Left means the left side first. Which one's going to be first in here? There's nothing on the left, so 6.5 goes. Then the right subtree. Then I read the node. then the right subtree. Is that going to come up in order? So in order, it's left node right. What if I want the elements in the decreasing order? Right node left to be decreasing order. So once I build this tree, the magic of this tree is that I can do a lot of useful things with it, like sort the elements. How do I insert an element again? We already done that. I have to go from here. I do a search effectively. When I want to insert something, I start in here. I'm looking for a value. Right? Once I found the spot, I can insert it in there. How about deleting? That's for the honest problem. Let's not do that. I want to ask if I solve this list versus array problem. How long is it going to take in this tree to find the spot? The worst case.
The same amount of time it takes for a binary search.
If this tree has a number of layers, it's called depth. When you hear the depth of the tree, it means how many layers it has. Is it true that in the worst case, the amount of search will take the amount of layers? Because every search goes down little by little to the leaves, right? So the worst case is going to take for search is the amount of depth. I say on average, that is log n. Like those trees, on average, take about log n, which means I can do the search for the spots just like in an array with binary search. How long is it going to take to insert? Remember in the list, insertion was really good. It took constant time to insert. Is that true in a tree? Once I found the spot, I can just put the element in there. You guys see what I mean? I think this thing has the advantage of an array in terms of finding the spot and the advantage of a list in terms of inserting the thing. However, can I have a really bad tree? What happens if somebody produces a tree that looks like this? I'm going to draw it here. I start with 1, 2, 3, 4, 5, 6. Is that a valid tree? Yeah. That's what? That's just a list, right? I didn't do anything. It didn't buy me nothing if my tree looks like that. That's a bad tree. It's a list. So this balancing property is essential for trees. For the tree to be useful, the number of layers has to be about log n, which means it has to be roughly balanced. So a lot of smart people have tried really hard to make sure the trees are balanced, because if they're not, they're just getting a list. But if they are balanced, they're amazing. So that's your honest problem. How to manage the tree. And how to do insertion, deletions in orders, and so on and so forth.
Such an asshole.
If you have a uniform distributed values, distributed into buckets, then you can count on the fact that each bucket has n allocated. Or you insertion sort the ones in the bucket. It's not too bad because they're very few. But then they're already sorted because then
Yeah, so like in funny,
so that's where this property comes in.
a tree should be one of like node.
Come with me.
Something like that.
Yeah.
So it's a separate data.
4? Oh, yeah, that's pretty interesting.
So then you can get like empty node if you take it a node. But like, it doesn't have a left. Yeah.